Hey there, how's it going, guys? This is our quality project for IME 430. This is by Spencer Harrison, Ben Siantar, Osia Flores, Stephen Dallezotte, and Jaime Guerrero. Thank you for listening. So, uh, in terms of our quality problem, we're really looking in at the defects of PCBs produced by the circuit board incorporated. We were in search of the root causes of failure for these PCBs. They really just were failing testing, and we were trying to find out the symptoms behind it. The sources of the problems included damaged traces, damaged parts, handling, and soldering issues.
All right, so to understand the defects in the system, we decided to create a cause and effect diagram. And in the cause and effect diagram, we kind of separated into categories: measurement, materials, method, environment, manpower, and machine. Some of these could be like lab error for measurement, raw materials and materials, unclear methods, different environmental things that could be problems in assembly, manpower, so things that the operator could have done in creating the PCB, or machine failure.
So after the cause and effect diagram, we determined that our events for defects were bad testing, soldering, bad handling, damaged traces, bad laser marking, missing components, and wrong settings. We then took data from a random week. We then took the data from the check sheets and developed a Pareto analysis and determined that our from this analysis that our damaged traces and soldering are major problems, or compose our like 80% of our defects. Furthermore, that we're going to be collecting data for the next 52 weeks, and just to make sure that this is not an outlier.
We wanted to see if there's a difference in the variances between the soldering and the trace defects at Circuit Board Incorporated. So our null hypothesis was that the variance of the solder is equal to the variance of the trace defects, and our alternative hypothesis was that the variance of the solder is not equal to the variance of the trace defects. We used an alpha level of 0.05, and our ANOVA test showed that our p-value equals 0.001. On the left, you see a graph of the damaged traces next to the soldering. Based on our p-value of 0.001, we can say that at a 5% significance level, we will reject the null hypothesis. In other words, there is not enough evidence to prove that the variances between the damaged traces and the soldering are equal.
After understanding that the variances were not equal, we went ahead and did a further analysis and looked and did a p-chart of damaged traces and soldering. From the p-chart, we noticed that the damaged traces were much more out of spec and needed much more looking into. So our recommendation for the trace defects is to discuss with the supplier about the panels that we are getting and looking at fixing these defects. Also just looking for new suppliers if we possibly have to just go to a new supplier for this. And third is checking out revising our acceptance plan for all these incoming lots. If we're pretty much taking in these poor quality products, we need to maybe have a better acceptance plan. And finally, for our soldering defects, really I think we should just calibrate the machines better and retrain the technicians to fix these defects, and just because of how small of a variation there is.